All right, so I'm Mohammed Asim. I'm a senior transportation engineer with the city of Calgary, Alberta, Canada. And I'll be talking about the connected vehicle approach to improve the bus queue jump operations. And we will be relying on the centralized TSP for that. So this project was done by my colleague Ahmed Abdul Nabi and myself. So he's not able to make it, so I'll be presenting on his behalf as well. Okay, so I'll start with a brief introduction to the city of Calgary and their plan around the TSP project. So then I'll describe what is a QGEM, what are their issues, and how we are going to improve that using this new approach. So I'll be sharing a case study with you guys that we did using the WISM model. Okay, so Calgary is one of the largest city in Canada with population over 1.3 million. So it's also, you can say, a center of oil industry in Canada. So this is a very beautiful place. So people from around the world, they come to here every year. And the city is also famous for its Calgary Stampede, which is the greatest outdoor show on earth. Okay. And also it's famous for its severe winter as well. Okay, so a bit about the city of Calgary. Okay, so it consists of, you can say, many departments. And for this project, so Calgary Transit, which is the one business unit, and operations department is the other. So we collaborated to come up with this new idea. All right, so a bit about the Calgary Transit. So Calgary Transit is one of the largest and well-utilized system in Canada. So with the daily ridership of over 1 million trips. Okay. And it consists of over 150 regular bus routes, express routes, and the rapid transit network consists of 2 LRT lines and 7 BRT lines. And we also have the on-demand service for the new communities. On the other hand, mobility operations, so they take care of overall traffic operations on the roads. So like traffic signals, timings to maintain them, detours, and incident management. Okay, so here we are. Ahmed works. So Ahmed is a traffic engineer with the mobility team, and myself will Calgary Transit. So we're both work on this project. Alrighty. So transit signal priority system is kind of a system which provides or grants priority to the buses which arrive at the signalized intersection by changing the signal timings on the go. So this system helps improve the travel time reliability of the buses. So in Calgary, so we are currently using infrared-based Opticom system. So this system works on, you can say, 2 pieces of equipment. One is installed on the buses, which emits the call when the bus arrives at the intersection. And there's another piece which is installed at the intersection itself, which receives that call and transfer that to the controller, and the signal priority is executed. So this system is providing us a very basic TSP functionality, but there are some other operational issues, like its reliability is low in terms of accuracy, and its cost is very high. So to address those issues, so the city is switching to a centralized TSP system. So this system works based on the existing infrastructure. Like it will use the bus location from the GPS system, and it will transfer or communicate that information to the cloud using the cell modems. And in the cloud system, it will store all the data. It will compute that as well based on the different parameters and logics. And based on that, it will assess like which bus requires TSP, in which direction, at what location, at what time of the day. And then that call will be transferred to the signal comm system, which is a TransSuite right now, the system at that city. So that system will send that call to the intersection remotely. So this whole system will be executed within a fraction of a second. Okay, so in addition to providing the basic TSP functionality, so this system has many other applications as well. So with this project, so we are gonna So we have actually tested this technology in the virtual environment using Vissim on the bus queue jump operations. Okay, just a bit description what a queue jump is. So queue jump is a transit priority measure, which lets the buses bypass the queues of the general traffic. Okay. And it consists of two pieces of infrastructure. One is the approach lane, which is dedicated to the buses, and there is a separate signal controller, signal head actually, so which regulates that. So in Calgary, so we use pavement loops to detect the buses when they come and occupy this lane, and based on that, it will you can say provide that special phase within the cycle, and the bus can say enters the intersection and clears it. Okay. So with this existing system, there is some kind of issues. So sometimes it is very useful. So it helps buses to bypass the long queues, right, and save some time. But depending on the bus arrival and the signal phase or the status, sometimes the drivers, so they end up experiencing more delays. So you can say, so this is kind of a dilemma zone, right? So sometime if the bus is arriving at the right time, it will get the green phase for it and clear the intersection. But sometime if it is entering or arriving at the wrong spot within the signal cycle, so it will end up experiencing more delays. Alrighty, so we did the case study at the same intersection. This is 114th Avenue and Barlow Trail in the southeast of Calgary. So this is mainly the industrial area, so lots of traffic. So these are the dominant traffic movements in the morning peak. This is in the afternoon peak, and this bus queue jump is located on the westbound approach. Okay, so these are the heavy bus movements, and the heaviest one is along eastbound and westbound direction. Okay. And these are, you can say, very high level view of the queues during the peak periods. So you can see along 114th Avenue, we have all red, so reaching up to 0.5 kilometer. And the queue jump again is in the westbound direction. Alrighty. So right here, so this is something new we tested. So we try to model the behavior for the drivers, so who arrive at the intersection. So they have a choice every time whether they should use the queue jump or they just stay in the general travel lane. Because drivers, so they are on the road many hours every day, so they develop their own kind of a criteria like when to use it and when not to use it. So we noted some observations in the field, and based on that, we come up with this criteria. So the driver, they might be thinking once they arrive, they first will check what's the status of the traffic light, whether it's red or green. If it is red, then they might consider, okay, whether the traffic is moving or they are already at standstill, right? And also they would see like what's the condition of traffic on the cross street, right? So if the cross street is full of traffic, it means the fresh green for that approach. So it will take longer to come back to the green phase on their approach. And also based on our existing condition, they would say like see whether the queue jump is already occupied by a bus or not. If it is already occupied, maybe they will not use it. Okay. And in the Vissim, so we model it using the PT partial routing, and we also added the UDA, user defined attributes. So where we put these conditions in, like the acceleration, the speed, and the traffic delay on that approach, and the occupancy. And this is a small part of the simulation, which will tell you like how the drivers are deciding whether they should use or not. So the buses. Yeah, over here you can see the buses coming right over here. So right now, Yeah, so right now, so the driver would have decided to use the QGEM because this red light on the westbound approach was fresh, right? And you can see there's lots of traffic on the cross street. So that's why the driver decided to use the QGEM. But if you see the following buses, it's not playing. Alrighty. So this next blue bus over here, it did not use the QGEM because it was already occupied by the other bus. So now it will get the green after this phase. Yeah, so the bus got the priority, it's clearing the intersection. So now you will notice the following buses, they will not use the QGEM because they know like you can say the delay on this or the red light has been there for a while. So they can get the green on this lane quicker. Yeah, there was a quick demo. Alrighty. Yeah, so this model was fully calibrated using the travel time for traffic and also for buses. And for the signal controller, so we use the max time. So max time is a software for Intel signal controllers. Okay. So now I'll just quickly fly through the results. I'll just tell you what are the strategies which we tested over here. So for the existing conditions, so we had a TSP in the eastbound and westbound direction, and it was you can say coming every 3 minutes. So there was a window of 3 minutes. So within that 3 minute, it can only serve TSP once. And for the Q jump, so we had a very short phase. So yeah, very short phase, and it was only for one bus. So about 5 seconds of green time, followed by 7 seconds for the clearance time. All right, so we also tested like, let's say if there is no TSP, what will happen? So, and we found that if there is no TSP, it will be worse for buses. Okay, so over here, we made some changes in the TSP business rules. So we increased the time. So previously it was 10 seconds. So now we made it up to 20 seconds plus minus. And also we increased the service frequency. So before it was serving every 3 minutes, but now it was serving every 2 minutes. And for the westbound direction, we made it 1 minute. So it was serving the buses every 1 minute. And we also increased the phase duration for the QGEM. So right now, like you said, before it was serving only one bus, but now it can serve 2 buses. Alrighty. So after this, we did some more changes because when you make one change, it will impact other traffic or movements. So over here, so we changed the green splits for other phases to improve it a bit. So over here, so we increased or extended the call on time. So in the original scenario, it was 10 seconds. So the bus was placing the call 10 seconds ahead of the intersection, but now we made it 20 seconds, a bit more aggressive. Okay, and finally, so we kept everything else which I described earlier same, and we added one more condition that was skipping the traffic phase, so which was with a low volume. It was eastbound left in this case. All right, and here's a summary of the analysis. So we focused on the delays of buses which are using the QGEM and the total transit delays, and we found significant improvement in the results if you compare with the existing one and the aggressive TSP strategy. You can see the delays on the QGEM reduced by almost half, and the delays on, you can say overall delays reduced by 1/3. Alrighty, so based on this study, so this was all in virtual environment. We didn't do anything in the field except collecting some data. So we can say like centralized TSP is an innovative and cost-effective solution to achieve the, you can say, kind of a functionality of connected vehicles without actually buying the buses, which are that smart. Okay. And we applied that strategy or technology for the bus UGMs, and it helped a lot saving the delays and making them more efficient. And all this was possible because of Wisdom software. So thank you PTV for having this model. And lastly, is just one observation. As I mentioned, like so we modeled the signal controller using max time, but we also tried that with RBC. And like with RBC, there are not many options. So we found it like so RBC can be used for simplified kind of a TSP modeling, but for more complex, it's better to use you can say controller-based software. Like in this case, we use max time. And what's next? So we are actually going to start the testing in the field. So we are in, I can say, very final phases of hiring a vendor. So they will actually test this technology in the field. And so we'll be testing that at the same intersection as well. Alrighty, that's pretty much I have. I hope you are not bored with this one. Happy to take your questions.